this about, right? One of my motivations in this is that I've, for a very long time, always wanted to create a game called Quantum Pong, where you take a wave particle and you do something fun with it for educational purposes, right? Here on the screen you see an animation of a wave packet, and you could try and think of all kinds of interesting game mechanics for that. Make it solve a maze, or just do literal Pong with it, or something of that nature. But if you're playing around with that, of course the question comes up like, how do you simulate a relativistic electron wave anyway? And there's a bit of a bleak picture here, right? I did applied math, and I've done all the classical wave equations, and there's lots of stuff out there, and it works really well. Then you have the Schrödinger equation, which is already not as great. The methods are all kind of finicky. And then I've often tried to find, okay, but how do the real physicists do it that want to do the real electron wave function? And it's kind of, as far as I can tell, there's just really not much out there at all that I could comprehend in any case. So if it comes to sort of the more general question of multivector valued relativistic waves, it seems perhaps like a pretty hopeless thing. But one of the things, this is perhaps a slightly more bleak picture than it really is, because there is one relativistic multivector valued wave equation that actually has a discretization method that works really well. This is the Yee scheme for electromagnetic waves, and it's been invented in the 60s. People still use this today because it's a really elegant scheme in a way, and it just works really well. So I thought, let's rewrite this in a more geometric way, because the electromagnetic wave equation is fundamentally quite a geometric thing, although this particular way of looking at it doesn't make it very apparent, I would say. And this is kind of a schematic representation of what the inspiration behind the Yee scheme is. And the classical Yee scheme kind of encourages you to think of magnetic fluxes on faces and electric fields on lines, which is kind of the wrong picture. If you really want to look at it geometrically, you have to think of the electric field as also a bivector swept out in time. And well, why do we want to look at this? Because if you look at the math behind this, then the Maxwell equation and the Dirac equation, the differential operator is actually kind of the same thing. And some people call this thing the vector derivative. I really like to prepend geometric before that, because it's a very geometric thing. And there's also the exterior derivative, which is also a vector derivative, and that's not what we're talking about. So geometric vector derivative, but what is this thing anyway, right? It sounds complicated. Maybe it's not really going to help us at all. But when I first learned about this concept, I was kind of amazed by how simple it actually can be, I think. So I've made a little animation of how one way of thinking about the discrete geometric vector derivative. And here on the right, we have a n-cube grid, as we call it, a grid of cubes, in this case two-dimensional one in x and t, because that's the biggest one we can plot on our screen. In the middle we have a geometric product, and then on the left we have all the vectors in our algebra. And if you write out that product between these things, make a little animation, then you're generating effectively this set of equations, whereby we're looking here in this case at a one vector valued field, so only the lines. We're ignoring the points and the faces for now as our field. But yeah, if we write out all these multiplications, and you have to think of this as kind of a convolutional operator going over the entire grid, you can kind of summarize that in this type of equation below. Okay, does that help us? Well, we're going to try and turn that into code. And that only takes a few lines. So let's see, we have here basically, is it visible? I think I wanted to zoom this in a tiny bit. Is it decently readable like this? Okay, then I'm not going to bother figuring out the zooming again. All right, so we basically have the same structure of equation that I just shown on the screen. We have an interior derivative of t with respect to t, and an interior derivative with respect to x of x, and they're both things of grade S or scalars, and so on, exterior derivatives for t and x and t. And these are very simple operators, so these are just simple upwind and downwind finite difference operators, nothing more to them, and this whole EDT thing is just an in-place array update. And then if we run that, there's a little bit of boilerplate below to do the plotting, but then that's not very interesting. So we get something like this. We initialized it with a, excuse me, how do I drag stuff here? There we go. I'm using someone else's laptop, excuse me if it's all a bit clunky. We set it up with an exponential of a quadratic in the middle, so an impulse response in the middle, and we let this thing run, and what we see is like two wave packets moving in x and t across this xt diagram, and it's a periodic boundary condition, so it goes around and it just will keep going around like that forever. And it's important to appreciate that this code doesn't just look like the math. In fact, this code is an exact realization of the geometric relationships we generated by performing this discrete geometric product. There's no approximation. This is an exact realization of the mathematical principle. If you look at this thing here on my screen, if you take the geometric product with the one vectors, you're going to get 0 everywhere. So that's kind of a cool thing about all of this, I believe. And we can do this not just with this xt space. We can do this in all kinds of dimensions, and I've kind of hidden these operators behind this little helper method to make things a little bit cleaner, sprinkled on a slight little bit of syntactic sugar, so the brackets are nicer. But it's basically the same thing. We have here the geometric vector derivative of phi, where phi are the bivectors of sort of your classical space-time, if you will. What we get out of that is this block of equations with interior derivative terms and exterior derivative terms and interior derivative terms. So we have here all the terms of grade x, y, t, and then we have the exterior derivative with respect to x of yt, and then minus y xt, because we got to reorder them and do one swap to get it in the canonical order. So these terms are just all the terms that are in the geometric product of these differential operators and the field. And if we run that, again, we're not really doing anything here except for recasting a 60-year-old algorithm into geometric wine bottles or whatever. We get a wave or a slice through a 3D volume. We've got here, you see the periodicity in Z, waves coming around. All looks nice and colorful. And we're doing the same thing, right? We got a little impulse response of a Gaussian blob. What else? And what are we really looking at? These colors are the first three components of phi. So that's the spatial bivector components. So that's, in this case, the components of the magnetic field. So that's what we're looking at. Looks nice. I think I want to go back to the presentation here for a second. So yeah, so we, like, without any proof or anything, I'm just going to state here sort of the general principle that this works for all grades and metrics. Yes, exactly. So, well, boring, blah, blah, we form the product. Well, the important part is you can always form this split between having a slice of time-like variables and a slice of space-like variables, and given these, you can find this one, and you can find this one, and you can find this one, and it never involves any approximation, and this is very much due to the geometric product if you go into the details of why it all works out. Because of the geometric product structure, you always have this leapfrog structure that allows you to have this causality, whereby if you know one slice in time, you can, all the other ones in time are implied as you march through time. So here we have this guy again on my slides. But now we want to go back to the code. So of course, if you're looking at this, you're saying, hey, we have this thing here, geometric looking, 6 bivector components. I'm claiming it works for all grades and whatnot. We were kind of interested in the even grade algebra as well, so let's go there. Let's write this out for the even grade algebra. And it actually looks kind of simpler in a way, you might say, than the bivectors. We've kind of filled out the whole grid of numbers, but we're not doing anything different. It's very much the same code, and if we run that, it doesn't look that spectacularly different from the bivector equation. We got a wave traveling at the speed of light around a light cone. Colors are slightly different, but it's non-trivial that it works in the first place, right? It's not exploding. We got beautiful colors, so something going on here. But let's move on from that. Let's do something different, or actually something that's kind of the same. Using the same algebra here, 3 spatial dimensions, 1 time dimension. Just renamed the Z to W, so that doesn't change anything. Still talking about the even grade subalgebra here, 8 components. The reason I've renamed it to W is because before we had a cube of 64 by 64 by 64. Now I've just squashed it down. I've squashed down the Z dimension to make it a very small dimension. And that might sound kind of, not interesting. But if we run that, and I should run it first and then start talking, I think. I don't want that. If we run that, you can see it looks qualitatively quite different. And if you were paying attention, it seems as if these things are actually not moving along the light cone. It seems that they're moving slower than the speed of light, actually, which in a sense they aren't, but we'll get back to that. But in any case, it's already pretty cool looking. If you were looking for fancy animation in your game, something to look sciencey and quantum-y, and you want to create a texture on your wall, then it was already, this would already be pretty useful, right? And there's another thing we can do. So let's see, comment. So before I kind of shrunk down the whole thing flat, but now I've given a bit of a spatial profile, if you will, to the squeezing of the space. And essentially I've relaxed the restriction that we were convolving all these unit length vectors across our grid, but we're using a slightly different length vector for W in every location. And if we do that, we get something that is quite strikingly different, right? We have a really confined wave packet, if you will, which is perhaps to some physicists very obvious. If Kaluza and Klein might have something to say about this, but we're not going to go there. We can direct the wave by manipulating the shape of the length of the vectors of W. And there's more we can do with that, because I have this default initial condition here, but if we switch over to another initial condition, so this one was where I had an impulse applied to the field at the center of the potential of this quadratic that I made. Now I've offset the quadratic and the impulse a little bit, and then you get stuff like this, right? It's sort of a classical, well, not a classical, but, well, depending on your interpretation of the word classical, particle trapped in a well, in a potential well, right? Except this is not the Schrödinger equation, right? We're looking here at an equation with what is it, 8 field components that are all actively participating in whatever it is that you want to believe this thing to be. In any case, again, it's excellent material for making cool animations with, for starters, right? So let's try something completely different. Moving on, so let's try a 2D equation for a change. And to spice things up, I'm going to make this the full algebra, so all the elements of the algebra of x, y, t. And to make it even more interesting, because, Schrödinger and Dirac, they both also did something like this. There's not just a first order derivative, second order derivative, but there's also term somehow proportional to phi. Let's also throw that in there and see what that does, right? And let's see, no problems here. Looks remarkably similar, right? And wait, did I even run the right file? Yeah, it does really look remarkably similar. And that's kind of interesting, I find. So this is not just a superficial similarity. As a matter of fact, if you have a field with the minimum amount of non-trivial dimensions in W, which is 2, you can decompose the field into a component that doesn't vary over W, which I call here light-like, which is, a +1 constant in W. And the rest that's left over is sort of anti-symmetric in W. And if you think about what the derivatives of these things with respect to W are, then the light-like part does not travel along the W at all, so the W is irrelevant for the light-like stuff. And the massive stuff sort of maximally travels around that compact dimension. And you also have the result that those derivatives are proportional to the thing itself. So if you look at the structure of these equations of the even-grade algebra in the 1-up space, the W plus x plus t plus, versus the geometric vector derivative plus a zero-order term over the full algebra, and you see that this last column, the derivatives with respect to W, are actually proportional to these multiplications by m, which is phi itself, right? And then, of course, if the derivatives to 0 with respect to W are 0, then you get this, which is just the thing without the W. So I thought that's an interesting result, personally. And let's go back to the code to look at some more examples. So I said any dimension any signature, no, not any signature, by the way. So we want to go higher, right? 5-dimensional. So we have a regular x, y, z, and t, plus an extra compact dimension w, 5-dimensional. If you write this out, it looks like this. It worked the first time when I tried this, or it worked the first time after I wrote a little code generator to write this expression for me, but we still have the same thing, right? We have everything that does not have t updated in terms of everything that does have t, and everything that does have t dependent on everything that does not have t. The structure still works out in the same way. What does that look like? Let's turn this back to true. Well, first of all, I said I was going to run them first and then talk about it. Sorry about that. Click, click. What? Click, click. Interesting. Okay. I am not at all sure what happens here. Excuse me, live demos indeed. Seems like it's just ignoring my run command somehow. Maybe I should. Oh wait, did I still have a figure open, that's the issue here. Sorry about that. It just went into the background because I clicked once too many, and now I've clicked 500 times, and maybe it's going to be even worse. Well, okay. Well, there we go. I don't know what this is, but it also looks cool, and it works. It does not explode. You get a sense of something rotating around the vertical axis here, right? And this, by the way, is also in a potential in W, right? So it's trapped inside of a potential in W. And yeah, just the fact that it works at all is to me kind of an interesting. Oh yeah, there we go. Oh God. Let's see. Can I interrupt this because I clicked like 10 times, I think. Okay, let's just bear with this for a few minutes, rather than deal with whatever problems might arise if I completely restart everything. Yep. I think we're almost there. Okay, so yeah, let's switch this around. Try a different initial condition, just for curiosity's sake. And if you look at this one, it's like kind of less visually spectacular, but you know, if you happen to know any quantum chemistry, you might think, hey, this does look a lot like a superposition of S and P modes of an electron wave, right? So, which raises kind of the question, in this higher dimensional space, is there actually a functional model of an electron hiding in there? And that's, well, probably a question you could debate for a long time, and I don't profess to have an answer to it. I think based on sort of my mathematical understanding of things, I would say this isn't, this equation what we have is not actually what Heston has said, so I think there's meaningful mathematical differences there. But yeah, make of that as you will. At the very least, you can make pretty looking things with it, right? And again, this is just the geometric vector derivative is 0 with a compact dimension to give us sort of the mass-like behavior. For contrast, it's also kind of interesting to, so let's take the same algebra, but now just the bivectors. We get a somehow not as nice looking equation, which is sort of less symmetrical, but it does work. But you can't really get this thing to very much look like an electron wave, right? It does seem like there's something essential about the even subalgebra in terms of getting it to behave all electron-like, if you will. Well, maybe a smarter person than me can find an initial condition here that does look like an S or a P wave, but I haven't been able to. Let's see, I think good time for a switch back to the presentation. No, not, more code. Okay, something different to talk about, kind of illustrate the idea, the difference between a light-like and a massive wave, right? So what we've got here is W, X, Y, T. So two non-compact dimensions and a W, so we can do mass, if you will. But we're actually not really gonna do anything interesting with the mass. We're gonna just give it a constant value. So there's no variations in W. I said I was gonna run it first. Let's take my own advice. So we have a massive wave, and this one is also kind of a trapped mode of a wave, but it's not trapped by potential formed in a distortion of W. we've done something else here. We've applied a little dimple to the length of the vectors x, y, and t. And to be precise, what we're saying, like here in the middle is the maximum distortion, and the length of the vectors t here is 1/2 the length of the vectors far away from the dimple. So you might say, popularly speaking, that clocks here in the middle will run at half the speed as they would run outside of there, and that has an effect on the wave function, and it traps the wave function. And this is a pretty extreme time dilation, if you will. This is like a slowing down of time by a factor 1/2. That's sort of associated with the density of the surface of a neutron star or something, so you can't really fault this massive particle to not escape from there. And this is not very theoretical, right? We know this happens. This is physics that you can measure by shooting a satellite into the sky. Gravitational time dilation exists, if you want to call it that. But now what's interesting, instead of focusing on the massive part of this equation, we can sort of say, well, get rid of the massive part and let's look what the light-like part does in the same setup. And, well, what do you expect? You start a little blip inside of this potential well, and it's slowed down a bit, and you see the wave redshifting, getting longer as it goes out of the potential well, but it gets out of there eventually, and then we got our periodic boundary conditions, and it falls back in again, all kind of as expected. But now it's kind of fun to see what happens if we take 2 neutron stars. We halve the speed of time again. I'm not sure if that's the math there is entirely right, but it doesn't matter. We slow down time by a factor 4. And now what happens to our light waves that start out in the middle of all this? They're slower in the first place, of course, so we're going to have to exercise a little bit more patience. But they're moving outward, right, because they're not really going to turn around. That's not what light waves do, except that, well, you know, if you were an observer sitting somewhere here and you were trying to detect something happening there, you're going to get pretty bored, it seems like, right? So what seems to be happening is that the light kind of prefers to orbit around this thing that we've created instead of going out of there, which you know, is an interesting dynamic, let's put it that way. And what I found especially interesting, if we take a one-dimensional setup with the same distortion applied to it, and I'm bringing all of this up just as an illustration of why I think it's interesting to play with these visual results, not because I'm trying to make any profound points about gravity or what it is or isn't, but if you look at this in one dimension, then this doesn't happen, right? So you can't have something orbiting the black hole in one dimension. So in one dimension, it doesn't matter how big you make the distortion, unless you make it infinitely big and you slow it down to 0 in the center. It's just going to happily, you know, go in and out the other way again. But in 2 or more dimensions, things play out a little bit differently, which is quite interesting, despite the fact that there's no singularities in this simulation, right? And it's something that I had never thought about in this way, that I'd always thought that the essence of a black hole was the singularity, but actually to trap light, you don't need a singularity, which is something that I had never thought of. So yeah, that's the main results. I'm already sort of at my summary. So yeah, indeed, the Yee scheme can be generalized to geometric vector derivatives of fields of arbitrary grades and dimensions. We can use that to simulate both light-like and massive type of waves, if you will. And all we really need for that is a geometric derivative of phi is 0. We don't even, per se, have to get fancy and add extra terms to the equation, which I thought is kind of beautiful. And we only really need a small handful of lines of code to implement all of this. And I think more importantly, really, it's not just that it's a few lines of code, but it's also a very, very small self-contained set of conceptual complexity, if you will, right? Let's say I have kids, and let's say that one day they're at the age to have the talk, and they say, "Dad, can we talk about partial differential equations?" I would tell them, "Look, have you done your geometric algebra prerequisites? You know what a geometric product is?" And they might say yes, and then I would say, "Well, it's pretty easy. You take a bunch of one vectors, you multiply them with your field, end of class, right? Done." And you know, they're kids, so they might complain, and they might say things like, "But Dad, I don't care about like light-like or massive waves. It's not my thing. All the kids at school talking about diffusing the heat equation. When are we going to talk about that?" And you know, at this point, I would have to be strict and say, "Look, you want to talk about exotic things like equations with derivative of mixed grades and all the complication that brings. First show me you can just multiply with one vector, and then we'll talk, right? I think that's the fair way of looking at things. But there's a lot of open questions about this work. So the relationship to any particular field of physical modeling, I'm not very qualified to speak on. And there's a lot of interesting questions you can ask about what other type of zero-order terms you can include in these equations, or what about interactions between fields, and so on. And to be honest, it also hasn't really brought me any closer to coming up with an interesting gameplay mechanic for quantum Pong, because that's really got a lot more to do with aforementioned interactions and how to deal with wave function collapse and the fact that these things just keep spreading all the time and making it hard to actually make a well-defined game out of. But yeah, it's been an interesting learning experience for me that I've learned a lot from. I don't know how I'm doing time-wise. I imagine, all right, yeah, I'm doing fine time-wise. So I have a bonus equation, can dig a little bit into that. So for instance, when I'm talking about different right-hand sides, right, different mass terms, if you will, if you have geometric derivative of phi, the geometric derivative toggles between even and odd grade. So if phi is even grade, then the geometric derivative of that is going to be odd grade. So I can't equate it to m phi. I need the full algebra to even make sense of that equation, right? Otherwise, it just trivializes if I have odd grade on one side of the equation and even grade on the other side. So if you insist on just doing an even subalgebra, and you don't want additional dimensions, but you do want a mass term, you have to have some kind of grade toggling term here. For instance, that could be multiplication by the spatial pseudoscalar, so that will also take phi to the odd grade, right? And you can try various things of that nature, and I've experimented with a lot of them, but they're not really part of the main talk because I can't say I understand and appreciate it all extremely well. But sometimes it works, right? For some signatures and some dimensions and some types of dualizations, it works, but it very often becomes unstable and explodes, and that's something that never actually happens with the pure geometric equation, because it's really just a conservation principle, right? You're just bouncing multivectorial amplitudes around inside of the n-cube, and you're never actually creating or destroying anything, whereas with an equation like this, it's much harder to prove that the thing even makes sense in the first place. But this one seems stable somehow, and also kind of quirky in many ways. But one of the things that is kind of not so nice about all of this is that we have to interpolate our field values. I don't know if I want to explain this, but yeah. Well, let's quickly go back to the slide. You have to do an interpolation step, because if you look at this picture, if you are forming an equation over the blue square and you've got all the things that sort of extrude under the wedge product onto the blue square, we're equating those things together. That works, and then if we add sort of an m phi to it, then we can say, oh well, that's fine. We just, in our update rule from the t at the bottom to the t at the top, we include a difference over the x's here on the sides, and we throw just a contribution in there from the bivector that we're stepping over, and that works out very elegantly. If you start multiplying with additional basis vectors, say you multiply with x to get a contribution from t, then the question sort of becomes what t, right? If I want to step from here to here and include not only the difference over t, but also something proportional to t, which one am I going to grab? Am I going to grab this one, or am I going to grab that one? Well, neither is a great answer, so the sort of natural solution is to say, well, you know what, we're going to average this thing, and then we could add it to that thing, but it's not as mathematically elegant, and also it doesn't always work fantastically well. Here's another one that's just in here because it's kind of beautiful if you want to see a non-trivial quaternionic equation with 4 components. I always kind of like the look of this one as well. So this is again a XT diagram of a particle trapped in a well. Yeah, and wait, did I go out of full screen here? I did. Let's go back. Yeah, that's the end of my talk. And if you're looking for a good geometric algebra library in Python, NumGI can recommend it. Also, there's an early write-up of this code and an attempt of me of writing this down on paper, which is very much incomplete, here at this link. And that concludes my talk. Thank you for your attention.